All right, next lesson is sound waves and matter. So what's the goal today? I can explain how sound waves are absorbed, transmitted, or reflected through matter and apply the knowledge to different situations. So first thing I want to look at is all forms of waves can be absorbed, transmitted, or reflected. Okay, and think of it in terms of water waves. So absorption. Absorption is the process where sound's energy is quickly dissipated by being transformed into other forms of energy. Okay, so engineers have accomplished this by using absorbent materials, so cork, heavy cloth, etc., and some odd-looking 3D baffles that reflect the sound until the waves get absorbed. So what you will have, you look at a concert hall, or if you're ever at the festival and you look at the back walls, it's very absorptive material. They don't want an echo effect. So the wall, on top of being made of some type of material, okay, it'll have an odd design, okay, and it might be as simple as um, just having kind of a cavity, all right, or it could be um, some kind of intricate pattern, all right. Um, so it might look like this. As if you stuck your fingers in, okay, it would look like that. And the reason for that is that the sound wave that approaches, so I'll do it in green. So here are my three sound waves. What happens is some of the wave will get through and absorbed. Some of the wave will get absorbed and what's left will reflect off on an angle, so you don't get a true echo. In this case, if you had a wave approaching, all right, some of it would reflect back, less energy. Some of it would get inside here and have more time for the material to absorb it, with less reflection again. So the wall design is kind of important in terms of sound or acoustical engineering, because they're trying to reduce that um, echo effect to a minimum. So when you look next time you're in a theater, you'll notice the majority of movie theaters use that heavy cloth or even carpet on the walls. It works very good as a baffle, and then you go to the more upper end or upper scale music halls, opera halls. Take a look at what the walls look like. And what they want is they want to make sure that echo is totally negated, so they will come up with different designs on the wall to help that material absorb the sound energy. So transmission. Transmission is the passing of sound energy from one medium to another at the boundary. Okay? So, as it moves from one to another, we know that our universal wave equation is FV equals F lambda. So when it goes from one material to another, what happens? Well, let's go V of the first material divided by V of the second material is equal to F1 lambda 1, F2 lambda 2. Now, please note, frequency can't change. Cannot change. All right, when you send out a pulse, okay, or when you create a water wave, you can't change the water wave later on. Same thing if you're in a band. If you play a bad note, it's not like you can fix it, it's gone. That bad note is played. So frequency cannot change once it's been created. So F1 is going to equal F2. So that means that in our equation here, F1 and F2, because they're equal, will end up canceling out. And we get a resulting equation or new equation that will calculate the new velocity or wavelength, depending on what we're looking for. And that just comes from the universal wave equation. So it's that comparative value. Okay. So using it, or an example, sound wave traveling through air, that's the velocity there. It has a wavelength of 0.75, hits the steel wall. What is the wavelength that's transmitted into the steel wall? Some will be reflected. Remember, you're going to end up with dissipation of energy regardless, because some will be transmitted, some will be reflected. I'm more interested in the sound that gets transmitted, what's its velocity. All right, so you have to be given three pieces of information or be able to calculate three pieces of information. So we're looking for the wavelength in the steel, so that's going to be number 2 for me, material number 2. So I know velocity in air was 332. It also tells me the velocity in steel is 5,000. I know the wavelength in air was 0.75, so I'm looking for lambda 2. So doing the math here, 5,000 would get multiplied up to the 0.75 divided by 332, and you'd end up with a wavelength of 11.3 in meters. So a much longer wavelength. Okay. Yeah. I was just thinking, just to show you, as an example here, just as a follow-up, if we do V equals F lambda then for air that we just calculated, we're told it was 332. If we look for the frequency when it's 0.75 meters long, we find that the frequency of this wave that was created was 443 hertz. And just to show that the math does work here, in steel, V equals F lambda, 5,000 meters per second equals F, and the lambda was 11.3. When you do the calculation there, you get frequency equals 443 hertz. So as your speed increases then, so I guess therefore, because frequency is a relationship between velocity divided by lambda, that would mean that as your velocity increases, to keep that same frequency, to keep that same relationship, lambda would also have to increase proportionally, so it still divides to be the same number. Or if your velocity slows down, lambda would have to get smaller as well. All right, because that frequency has to remain constant, so that proportional relationship has to remain true. So reflection is the next one. Again, there's an applet on the site for you to take a look at. So sound energy can hit a surface and be reflected back. However, the reflected wave has its phase shifted by half lambda, and there's two types of reflection. We have what we call a fixed end reflection. So in a fixed end reflection, what happens is that, and you see this when we do the slinky demonstration as well, but with a fixed end reflection, the sound wave that's approaching the barrier, all right, what happens with it being fixed ended, the resulting wave reflects out of phase. So it's going to look like this, reflecting in the other direction. Okay, and I'll put on here slinky demo. Probably by this point in time you should have, if you followed the order of the journals and everything, you've probably done the slinky demo already for yourself. So this is just confirming or putting it in your notes. And then we have what we call free end reflection, which means that black wall is not there. So basically it's let loose at the end. So the reflected wave, and it will reflect, okay? The reflected wave is on the same side. All right, so I just want to make a note to that then. So this wave is what we call half lambda out of phase. And out of phase because it's on the other side, okay? And this wave is in phase. All right, so again, if you've done the Slinky demo or the Slinky lab, then you've already seen this before, nothing new. You should have been able to probably anticipated that. So what about waves at boundaries? So what happens when we go, say, air to steel, as I was doing in the previous example? Well, if we go air to steel, and we're going to do a before and after. Before, and I'll go after, I guess, over here makes more sense. So here's steel before and after. So what happens at that barrier, so put the barrier right here, air and steel, air and steel. So we send the sound wave toward the barrier. And what happens is that that sound wave, there is reflection, and because the steel barrier is so much more dense than air, it's considered to be a fixed end reflection. All right, so a fixed end reflection. Because it's so dense, it behaves the same way. So we do get part of the sound wave is reflected, heading in the opposite direction, and then there is some transmission, a different size wavelength, all right, different volt speed. So here's your reflection, and here's your transmission. All right. So the waves, I've intentionally skewed them, drawn them a little bit different in terms of size and amplitude, just to show the difference between them. Now what happens if it's the other way? What happens if sound is coming out of the steel? So we go steel to air, and we'll go the same setup. We'll go before and after. And after. Draw your barriers. Steel and air. We'll move left to right, same way we read. Steel to air. Underline some headings here for you. So if it's coming out of the steel, here it comes, heading toward the barrier. What happens? Well, because we're going from dense to less dense, this actually acts as a fixed end, opposite fixed end, free end, and reflection because of the difference in densities. So what does that mean? That means that at the steel, you will get your reflection or echo in the steel, and you will get your transmission into air. And again, there'll be a difference in amplitude and speed and wavelength, reflection, transmission. That's because of material and energy loss and so on and so forth. Okay, so very important to be aware of here. So definitely something you can be looking at in terms of a test is being able to anticipate interaction or anticipate wave behavior at barriers. Oops. Behavior at barriers. I can't spell. I'm giving up here. Okay, so there you go. All right, so you have some of the homework assigned here. That's it for this lesson. Give those questions a try, and if you have any questions that you want cleared up, please let me know, and we will get them fixed as best I can.